the way the system works is that you have the cartridge, throw the water through the cartridge, and then you put that cartridge into the incubator. And the incubator will then grow the bacteria for a given number of hours, say 6 hours, and then you take that out and you put it into the imaging system, and the imaging system will autofocus and identify your colonies, the bacteria that have grown.
That was right from the middle of this week's episode, where our guest explains the solution offered by WaterScope. Hello and a warm welcome to yet another episode of the Mission Shunya podcast. Hope you are doing well today. Stay indoors as much as possible and stay safe. If you have been following Mission Shunya on social media, you would have noticed the recent announcement about the collaboration with Smart Sustain. As a regular listener, you would agree that I keep talking about the power of collaborations and working together to be a catalyst in this transition towards the zero carbon economy. It is in that pursuit Mission Shunya and Smart Sustain have joined hands. Smart Sustain is an initiative by Manjunath Gangadhar, a communications expert who has worked in the media space for a long time, covering many campaigns around environmental issues. Smart Sustain brings to you even more inspiring stories in the sustainability space. Videos from Smart Sustain are now available on the website of Mission Shunya as well. So do check missionshunya.com or smartsustain.in to know more. As always, do spread the word. Now on to this week's theme. Well, during these times, we really feel bad when there is no cure in sight for a virus. But do you know around 500,000 deaths annually are because of lack of access to clean water? Again, well, if you are in the developed world, this might seem like a no-brainer. You can probably drink water right from the utility tap. But did you know that 1 in 10 people in the world don't have access to clean water? The United Nations in 2015 announced the Sustainable Development Goals that aim to achieve a slew of goals, especially 17 of them by 2030. And one of them happens to be access to clean drinking water. That is Sustainable Development Goal number 6. And Sustainable Development Goals and tracking the progress towards it is a theme of the podcast channel. So on this episode, you will listen to the co-founder from WaterScope, a spin-off from the University of Cambridge in the UK. WaterScope has developed an inexpensive, rapid water testing microscope capable of identifying bacterial presence in water in less than 6 hours. That is 4 times faster than the current tests available. The technology is easy to use away from the laboratories and does not require the end user to be highly skilled. So let's listen in to the story from our guest, who is...
My name's Alex Patto, CEO and co-founder of WaterScope.
Alex, let's begin by looking at the idea behind WaterScope. So how did you get started with this?
Sure. So I was doing my PhD at the time in genetics in Cambridge, and I was currently doing it on... I was looking at motor neuron disease. I was trying to investigate a particular mutation in Drosophila, that a kind of a fruit fly that cause motor neuron disease in humans, and I was trying to understand how it kind of functions. So the reason I got into that was because I wanted to have some impact on motor neuron disease, and my nan had motor neuron disease, and I was affected by that when I was quite young, and I wanted to have a kind of impact in that. And I found myself getting more and more removed from the impact. So I was actively looking for something to get my kind of teeth into. And fortunately, I stumbled across this program at the University of Cambridge called Cambridge Development I-Teams. And what that does is it takes a bit of research done at the university, and they get academics, PhD students, undergrads, etc., to really see how that can be put onto the real world and have an impact. And the thing I was looking at was this kind of photocatalyst, or kind of powder that could purify water. And we were tasked with the kind of question of, if you purify the water, how do you tell whether it's clean or not? And I think I was the only biologist in that team at the time. And I kind of got stuck into looking at the existing systems that would test for bacterial contamination in drinking water. And I found that they were really, they were based on the methods you have in the lab, but they were really complex, and they were quite expensive, and also very slow, really, and quite prone to error. So me and 3 others at the time in that kind of team, we thought maybe we can come up with a better way of doing this. And the more we looked into this, the more we found that the reality is that 1 in 10 people don't have access to clean drinking water, and the majority of those people live in very low resource areas. So the system that had been developed over the last kind of 30 years and was considered the gold standard, and still is the gold standard now, wasn't really enabling or empowering the people who don't have access to clean drinking water to test their water themselves. So me and 3 other co-founders, we founded WaterScope, and we, with a simple kind of aim of trying to empower community members to be able to test their own water. And this was in 2015. It's quite a while ago now. And we started out with one of our co-founders, Dr. Richard Bowman, had developed the OpenFletcher microscope, which is you can find that now on openfletcher.org. But we had this kind of open source microscope, and we used this to get a very early proof of concept, being that using a microscope we can identify bacteria much earlier than by eye, and using the Raspberry Pi and other off-the-shelf electronics, we can automate that process quite significantly. So you don't need to rely on the user's expertise in terms of what a bacteria looks like. It reduces that error in that front. And also we found, so that kind of automated one part of it, but also we found that the most complicated bit in water testing is actually preparing your sample. So if you imagine you've got kind of a tap of running water, and the WHO guidelines, their recommendation of whether water is safe to drink or not is detecting a single E. coli in 100 mils of water. And that's like looking for a needle in a haystack. And when you're preparing that sample, you have to be really careful not to contaminate your sample, because as you can imagine, there's bacteria in the air, there's bacteria in your skin, and the current process was very manual, which meant that it's really easy to contaminate your sample. And when your threshold of contamination is just a single bacteria presence, then it's, you can see how that may introduce a lot of false errors. So we then spent the last the next kind of 2 or 3 years trying to develop a cartridge that automated your sample process. And so what we're trying to do really is to make a system or device that is extremely easy to use from start to finish, so anybody can use it. So it's independent of resource and independent of your kind of the user's skill set or training. And we hope that this can allow community members and key stakeholders that are affected by water contamination to be able to test their water and to implement local kind of solutions into that.
That's a very good story. And having followed the story for the last few years, I really know the amount of the work that you put into this. Now, you didn't mention about access to clean water. And one of the sustainable development goals is access to clean water. And you have seen this problem on ground. You have been to many parts of the world. You've seen this problem, and then you've tried to develop your solution around the problem. And what is the reality in general when we talk about access to clean water?
Yeah, that's an interesting point. I think on that note, actually, one thing we tried to do very early was engage with end users or people affected by it as soon as we could. And we found from our first field trial, where we went to Tanzania, Dar es Salaam in Tanzania, and to various communities there, tried to understand the kind of reality that is on the ground. And we learned a lot from that first field trial, and we radically changed our approach because of that. We found that it was far more complex to conduct a test on the ground. The locations at which the water is, as you can imagine, were kind of that needed to be tested, really rural. So we became aware that we had to make our system much simpler, much more portable, and much more user friendly. And we really over the last kind of 3 years have learned much about the kind of reality on the ground. And the second field trial, which was in 2017, we went to one of the largest refugee camps in sub-Saharan Africa. So this is Nyarugusu refugee camp in the kind of west of Tanzania. I think it's got 150,000 people. And we went there with Oxfam, who kind of supply all the water. And we found out from them that they spent the last 20 years just trying to get enough water to give to the population there. And now they're looking at quality of water, and they have about 800 taps. So these are kind of village taps or household taps, and they test each one of these for chlorine and pH kind of every week. But actually, the bacterial testing that's done, they only test this once every kind of 3-4 months. And the reason for this is because the system they've got at the moment is too complex. So they have to drive from the camp to the lab, which takes about 3 or 4 hours. And there's also the added kind of pressure that you have to go within a certain amount of hours. So if you leave too late, there are bandits on the road. So you can't leave the camp when it's dark, basically. So it means that if you've got a 3-hour, so a 6-hour round trip to do tests, it makes it really difficult to kind of get the testing frequency that you want. And we find this is mirrored to various places we've been to. So we went to India in 2019, and we went to this stakeholder meeting, which involved various water testing agencies and government officials who were discussing the current methods of testing the water. And they found that it takes about 1 year to do 500 tests for bacterial contamination. And the reason this is because the training is quite high. So there's a lot of money spent on training, and there's a lot of money spent on it kind of travel and logistics. So we see this kind of the issue being that current tests do not enable frequent testing. We see this issue quite often. And further to that, there is also we find a big disconnect between community members or people, say in the camp, who are kind of drinking the water every day, and the NGO or the government who are doing the tests. So one thing that we want to be able to do, and we've been working with Oxfam to try and understand how we can increase our impact. And one of the ways is through behavioral change. And what NGOs like Oxfam want to do is they want to be able to go into a refugee camp or community, conduct a test with a key stakeholder, and do it with them. So it kind of show them how a test works, and show what a contaminated water source result looks like. And the problem at the moment is because the tests are quite slow, it means that they have to go away to process the test. So they go into the camp, they conduct a test with a community member, they leave, they may come back 2 or 3 weeks later, and that results in a significant disconnect between the kind of community members and also the NGO who have the information about whether the water is contaminated or not. And there's sufficient studies that show that if you empower people with the ability to conduct a test, but also provide a local solution, such as simple filtration methods or boiling the water, they will be responsive and start kind of correcting the situation somewhat. So we at WaterScope, we do believe that the best approach is by empowering people to be able to test the water and then solve that contamination themselves. And we see there's a real gap at the moment between a test that empowers them to do that and really provide that solution, if that makes sense.
That's a very good problem statement, and it's a very good gap that you identified. You want to bridge the gap. What I understood from the brief on-ground experience is to understand that time is a crucial factor for people to kind of, between the time they test and between the time they know results so that they can implement. Time is one crucial factor that you've tried to address, and your product actually does that. What are the other aspects? I mean, when we generally talk about product, it's usually quality, cost, and time. What about the other two, quality and cost, when you compare it to the other alternatives currently available?
Yeah, so quality is certainly one, and I would rephrase that to integrity, maybe, or integrity of the science. And one thing we've been trying to put in our system is make sure it maintains a strong scientific rigor, basically. So, and that goes hand in hand with simplicity. So we want it to be simple. It has to be simple, but it also has to be simple that it such that it maintains a high level of testing quality. And initially, we started out looking at things like local manufacturing and open source hardware, and we found that actually we moved away from that at the start a little bit because we found it very difficult to have local manufacturing and open source hardware and try and maintain the quality of that science. And I'm sure it's possible, but we found it quite difficult, quite challenging to do that. For example, the cartridge needs to be manufactured in a sterile environment. It needs to have a particular set of reagents in it that are manufactured in a particular way. And there's lots of quality checks that go into this. And we found that as the quality of a test is governed by how well that cartridge has been manufactured, and we can attest to, and Alicia, who's the head of microbiology in WaterScope, can attest to, a slight deviation or slight change in that cartridge can really hinder the result. So we found that we needed the test to be made at very high quality, and it has to be made in a way that we have adequate quality control checks. So this is what we're doing now, trying to understand what manufacturing techniques we need to use and what checks we need to put in there, and what tolerances we have at the moment. So that's something we've been trying to address for the last 2 years. So certainly quality or integrity of the system needs to be there because people have to be able to trust the result. For example, one application of our system, which we're trying to explore, is that as it's very simple to use, and as you can transmit data kind of over SMS or over Wi-Fi or Bluetooth, you can potentially you could loan systems to community members. They can conduct tests in their village, and their results could be sent or streamed to the central hub, be it an NGO or government. And you can somewhat democratize testing. So the community members can see the result, but the NGO can also check the result, make sure it's been done correctly, and also have kind of real-time monitoring somewhat. And that only works if you can trust the test is going to work 99.999% of the time. And this is something we're trying to ensure at the moment. And we put a lot of energy into making sure it is robust. Second to that, of course, it has to be cost affordable. It has to be affordable. Luckily, we know that the current systems are at a reasonable level of affordability in terms of per test use, and they range between 20 pence to about $3, or kind of £2.5 roughly per test, and we're well within that for our test cost. So that's another thing we've been trying to bear in mind, and it's something which is we've tried to address as we go along. So we start with the kind of expensive equipment, but then we try and find replacements that maintain the quality but are slightly cheaper. This is quite a long exercise as well. And then I would say, maybe just to reiterate, that the central thing we're looking to do is to make it simple. So we've tried to make our technology as accessible as possible. And this involves a lot of kind of human-centered design. So really getting down on the ground and getting people to use our system. We've done about 4 field trials now. And each one we have iterated and changed the system. And if you look at the kind of first prototype we had in 2015, the one we have now, it's almost unrecognizable. And each time we go on a field trial, it changes significantly. So we've got another field trial planned, actually in a couple of months, and we're going to do that remotely due to kind of COVID-19. But I expect it to change quite significantly there as well. But we think that's an important point to make sure that the end users or the people who will be using our system are as involved in the design process as we are, because they're the people who have the problem. They're the people who really know the nuance of the issues, and we're trying to learn from that as much as possible.
I would definitely be interested to see the new prototype. I mean, I was lucky enough to see the first prototype in 2015, so I'd be definitely keen on seeing this. And as you mentioned, balancing the quality and the cost is a serious challenge. But of course, considering this idea and entire thing came out of a hackathon kind of an event where people came up with different ideas, looked at various options that you could leverage and use. Technology has been one crucial factor in getting this product out. Can you summarize the technology differentiation in this product and the way it is manufactured as well?
In terms of how it's changed?
In terms of the technology differentiation that the product brings about, and in terms of how you put together the different technology. Like, for example, you did mention that you make it a connected device so that people have access to data, the NGOs have access to data. That is one part. But then, of course, you use technology like 3D printing. How has 3D printing enabled make the product better, if I could say that way?
First of all, I think the thing that has really enabled us to get to where we are now is one of our kind of things like Raspberry Pi, Arduino, these kind of off-the-shelf hackable electronic systems really enable us to start looking at, start testing this and start kind of playing around with different approaches. And also 3D printing as well. So 3D printing has allowed us to rapidly prototype. So we worked with a company called Stick Lab in Tanzania who manufacture 3D printers. When we went there the first time, we actually did a lot of rapid prototyping in the field. So really trying to understand how we contained our system and design it in the field, which that gives us a really quick ability to change our device and manufacture things. So the cartridge has probably been through almost about 100 to 500 iterations over the last 3 years. And that is largely thanks to the fact that we have 3D printing, and we can design something, we test it, we kind of redesign it, and that has certainly allowed us to be creative in what we're doing. And I can't imagine how we would do that without 3D printing and conventional methods. The skill set requirement is much higher, and I think we would have to get someone specialist on board. Whereas 3D printing, I've essentially learned that, and much the team members have also kind of learned that on the job as it was, because I'm a geneticist. I then went, after my PhD, I went full-time into WaterScope, and the first kind of month I just learned about 3D printing, and that allowed us to kind of have the capacity in-house, and much of our co-founders and people who work with WaterScope kind of learn things on the job. And I think that's an important part of being a startup, I think, and trying to be adaptable and responsive somewhat. So the kind of as this kind of ecosystem or environment is changing, it's much easier to start developing and testing these things out in places like Cambridge. For example, we worked quite heavily at Makespace initially, which is this you can rent a workshop. Basically, it's got 3D printers, it's got CNC machines, it's got laser cutters, and it really enables people to be able to start designing stuff and testing stuff out with a minimal training requirement. And I think that's helped us a lot. So the system itself consists of a kind of microscope, which is powered by Raspberry Pi. We use a Raspberry Pi camera, and then we buy some off-the-shelf lenses, and then we've essentially developed a kind of case for that now. So the prototype you probably saw in 2015 was this open Fletcher microscope that Richard Bowman is now taking forward with openfletcher.org. But we've really kind of taken the optics module of that, encased it in a kind of a robust case. We've added an autofocus mechanism, and we've also built our own incubator. So the way the system works is that you have the cartridge, throw the water through the cartridge, and then you put that cartridge into the incubator. And the incubator will then grow the bacteria for a given number of hours, say 6 hours, and then you take that out and you put it into the imaging system, and the imaging system will autofocus and identify your colonies, the bacteria that have grown. And we've been working with a kind of undergrad called CJ, who's been working on looking at how we can automate detection. And he's done a great job at getting machine learning to be able to identify colonies quite quickly. And we've really pushed the sensitivity of that quite a lot. So now we can see them much earlier than we could before. So by doing that, we can identify and also count specific colonies using machine learning. And I think that helps in part to make our system a truly kind of simple system. And again, that runs on the Raspberry Pi. So that without that, we'd have to make a custom unit, and that becomes really costly. And I think, these off-the-shelf parts and kind of very flexible kind of hackathon type systems are really enabled us to do this in-house quite quickly.
That's a very good summary of how the system works and what are the different solutions that you have adapted and what goes into the system, basically what goes in the system. That's a very well put. Now going to the big picture, you have done 4 trials or the four field trials. How do you plan to roll this out in the next few years? And if you were to pitch it, or if you were to quantify the impact that you foresee, what would that be?
So we're just coming up to design finalization now. So we've got one more field trial, we think, before we can finalize the design. We know that it works in the lab. So Alicia's done a good job at getting our baseline, understanding how it compares to gold standard lab methods in terms of sensitivity. We've just got a bit of user kind of design work to be done where we're trying to understand the kind of subtleties of how people use it and where the common errors are and where the common failures are. And this will be running now over the next kind of 6 to 9 months. And in parallel, we're looking at manufacturing now. So because the cartridge is quite, the design is very specific and it's got a very specific set of tolerances. We make that of CNC machining. And it's quite difficult at the moment to get that in high numbers to test it in the scale we want to. So we've started doing injection molding for the cartridge. And this is really the start of our manufacturing journey. So what we imagine happening is that we will have the kind of first run where we test it out, and then we may have to go back and redesign the mold, make sure that it works as good as it should do. And we imagine that happening now for the next six months to a year, where we try to really convert our 3D printed designs or CNC designs into injection molded designs or manufacturable designs. And there's a lot of kind of learning that needs to be done in terms of how do we do quality control checks, how do we automate the assembly, but maintain the cost, keep the cost down, but also the quality up. And there's a lot of kind of new avenues that we need to navigate in the next year. So the manufacturing is manufacturing and finalizing the design are really our top aims now over the next year. In parallel to that, we're looking at who our first customer is, and we, for example, we had a deadline that was trying to submit an application to the UNICEF, a request for proposal, and this was essentially UNICEF had released, and they've been trying to release this for the last 2 years, a call for faster systems, faster and simpler systems. So we see NGOs such as UNICEF and Oxfam as our first customers, and they forecast they currently do around 2.25 million tests a year, split between three different markets. One is kind of conventional regulatory testing, such as you do in a refugee camp or at the household level. One is behavioral change testing, which at the moment the market is quite small, but that's because the systems at the moment are not tailored for that market. So we expect that market to grow significantly. And this is where you kind of work with communities to be able to do tests and democratize testing somewhat, and really try and get that behavioral change, which leads to kind of sustainable change at the community level. And the third market being household surveys, and household surveys being where every 5 years they will do 50,000 households in particular countries where they take measurements like your children's height, what kind of food you have in your fridge. And one thing they cannot do at the moment very easily is what's the water quality like, because the tests at the moment are too slow and they require too much consumables, and it's not feasible to integrate that into the current program. So that's another market we're looking at, and again through NGOs and like Oxfam and UNICEF. And UNICEF are the largest purchaser of these type of testing systems. So we're trying to work closely with NGOs such as UNICEF. But second to that, we see there's a real demand for kind of government-led testing. For example, in India, the majority of testing is led by the government. And we know that they want to expand their capacity, and they want to expand their testing, and they're looking for other ways of doing this. And we see that as a substantial market we're going to try and get into after the NGO. But we see the NGO market as a good first market, as it kind of, we think a tick by an NGO such as UNICEF will really enable people to understand how our system works and give us credibility in that market. And then we can look at government testing and private water testing companies. And that's how we kind of see our kind of commercial kind of growth, being NGOs first, then we expand to governments. And that's kind of a really nuanced market where it's all about building relationships with the government and understanding how you fit into their kind of procurement systems, how they kind of conduct tests. And that's something we need to explore. And we see working with companies to do that as a good strategy. So us being quite a small company, I think we're at the moment a team of 8 or 9, we see working with partners who can help us commercialize it as a potential route to get there as well.
It's a good solid plan that you have. I definitely vouch for the fact that going with an NGO like a UNICEF is probably a good start. You'll probably have more data points before you reach to the governments, because governments will have their own set of procedures, protocols, and standards that you need to meet. So it'll give you a good exposure. So on a final note, Alex, you are a scientist, a researcher. You know you have developed this technology. And where do you see this technology being used outside of what its intended application is? Do you think this can be used in other applications as well? Do you think there could be other use cases for the technology that you've developed, and how is that panning out?
Certainly, we would like to explore other avenues. So we see that water testing itself, we aim to commercialize that in kind of 2 years. And there's ways of expanding it once you commercialize. So, for example, we can start looking at mapping and trending and how we can maximize our impact. But one thing we're looking at doing is can our technology, which essentially what it does is it takes the lab into the field. So it automates kind of petri dish culture into the field. And we think that has a lot of application. So one thing we're looking at now, and we've got a couple of grants to really explore this, is to say, can the system be used to identify things like urinary tract infections? Can it identify antimicrobial resistance? Because there's a whole range of applications where or kind of tests that rely on colony culture. For example, at the moment, if you go to a GP surgery in UK or in India, you will with a suspected UTI, they will then take your urine sample and send it to a lab. In the lab, they will do a testing process over 2 or 3 days with petri dishes, identifying what bacteria you have and also whether it's resistant to antibiotics. What our system does, essentially at a kind of basic level, it makes that colony culture step and enables that to be done in the field or in any location. So what we're exploring is, are there many use cases where people would like to be able to do colony culture or kind of basic microbiology in the setting that which they collect the sample? And one thing we're looking at is urinary tract infections. So can you identify what bacteria you have and what antibiotic resistance you have quickly and on site, so you can recommend the right antibiotics? And it's something we're doing with Addenbrooke's. So we're doing a proof of concept now over the next 3 months, trying to see how our system compares to the gold standard in the lab with real urine samples. Another way of expanding, and something we're looking at as well with other companies, is can we start looking at other bacteria? So what the cartridge does is it takes any conventional nutrient media. So for example, if there's a nutrient media for cholera, you can plug that in the cartridge and suddenly you can do cholera testing. Can you also do the same for Legionella? Legionella is a big problem here. It's a lot more complicated than just putting the nutrient media in, but that's potentially one avenue as well. So we're trying to be responsive in terms of what our system can do outside of water testing. And we see that as really kind of expanding our impact. So we can enable someone to do a very simple test for E. coli or coliforms in a water source. But can we also then, if that's positive, say, okay, is this now positive for cholera? And really look at the kind of nasties in water and understand what is actually there. Because E. coli at the moment is used as a proxy. But we see that potentially we have other avenues which we can expand into by looking at other bacteria using our cartridge. So it's something we're trying to look at, and it's something which the university is an excellent place to explore that. There are a lot of really good academics here that have an interest in trying to work with us to try and explore this, and it's something we're trying to do. It's a bit of a challenge trying to juggle various hats at the same time, and we're always conscious that we can't compromise our central mission, but it's something we're trying to explore as well, if that makes sense.
Perfect. I mean, it was definitely good to listen to the story, and I'm very much impressed on the last part where you're seeing applications outside of what you intend to do, but keeping your focus on enabling people have access to clean water. So if that's your core mission and you're pursuing it, so that's a good thing to know. But of course, as you said, when you develop a technology and when you're in a place in a research facility. When you're in a university, you definitely can find out if there is other avenues to where this technology can be used. So no harm in trying that.
It's definitely a double-edged sword, I think, because you see a lot of people, you meet a lot of people in the day, and you meet a lot of really interesting researchers, and you get tempted by a lot of things. And you have to. One thing that we struggle with, and we've got much better at now, is saying, okay, this is our mission, this is what we're doing. And because in PhD, when you're doing a PhD, for me anyway, you were kind of encouraged to be very kind of exploratory in my thinking, and that mindset in a startup, you have to be very precise and very direct. And I think that's something that took myself quite a while to understand and really respect. And I think now we have good system in place to make sure that we do what we set out to do, and we have a way of analyzing opportunities, and kind of the output really is how do they impact kind of our impact. So how does it cause us to have a greater impact or a lower impact, and we can really make educated decisions around what opportunities we can try and explore and which opportunities we should maybe pass on. And that's something that comes with, I think, a bit of expertise on being in a startup for 5 years, and that we kind of understand how to do things a bit better. And you learn every day a bit as you go along in this kind of journey. And I think it's immensely helpful to have such a great team around WaterScope, and I think the mission really helps us get that team. So yeah, we're quite thankful in that respect.
I can definitely tell you that you've been behind this mission for 5 years, and having seen the first prototype in 2015, and you're still stuck with the big mission statement of having this technology out so that people have access to clean water. So you've been through this, and you've come up with multiple variations, and you've developed the product. So good luck with WaterScope.
Thank you very much.
And thanks for taking time to be on the podcast. It was a pleasure.
Thank you very much for the invitation. It's always great to talk about it.
So, well, I hope you enjoyed the conversation. WaterScope believes in empowering people in remote locations to test the water themselves and take corrective action. The other point not to be missed from the conversation is the use of technology like 3D printing and the off-the-shelf components like Raspberry Pi from the market. The use of common spaces like makespaces to do rapid prototypes and get started is also worth a mention when we talk of spin-offs from universities. The links to connect with Alex and to know more about WaterScope are in the show notes section of the podcast, so please do check them. Now, on to this week's action item towards Mission Shunya. We'll stick to this week's theme and talk about water. Recently, I had to deal with some issues with the washing machine at home, and when I got it serviced, the reason turned out to be an increased hardness level, especially at the water inlet, which had caused some water flow problems. As someone who had access to utility water at home, we never had this problem. The water supplied was potable, but this incident was a wake-up call. As it turns out, the water hardness has gone up significantly in the city where I live. And a little bit of more search revealed that fluctuating water quality is an issue, and that is why governments like in the UK have mandated water checks from time to time. So, if you haven't checked the water quality at your premises, do give it a thought and call up someone to do the checks from time to time. I'm sure ensuring the availability of quality water is a big relief. And as always, if you like the show, do spread the word. Just a small help of sharing the episode link to 3 people in your network will go a long way in getting the message across. And it also just takes about 30 seconds to do that. So big thanks for that. So with that, this is Girish signing off. And as always, thank you for listening.